Okay, this is Network Engineering, Chapter 2, Part 3. We're going to look at DNS and streaming protocols. So the DNS, or Domain Name System, is probably one of the most important services on the Internet. Its primary job is to provide a lookup service for human-readable names and convert them to their IP address. As noted in the last lecture, IP addresses are typically expressed as 4 integer numbers, each one ranging between 0 and 255, in a format that's also known as the dotted quad address. These addresses are highly network specific. For example, 157.160.36.12 is a machine on our campus. But what does it do? Which machine is it? Who knows? On the other hand, most of us know what Sloop is. We've maybe logged into it. We've certainly heard other people using it. It turns out that Sloop's IP address is, not surprisingly, 157.160.36.12. Sloop is a lot easier to remember than that number. And it's that DNS that allows us to get the IP address for a particular name. I hate using metaphors for things, but it's kind of like having an address book for the internet. There are several really, really important and kind of interesting, frankly, features of this application protocol. First, it can convert the name to an IP address, and if the system's administrator desires, it can go the other direction. So it can take a number back to a name, which can be useful when you see somebody trying to hack your system. It also allows multiple names to be given to the same machine. These aliases are useful for naming services. For instance, maybe we start off with a single machine like Sloop that handles our web and mail traffic. So we create some aliases such as web.ship.edu or mail.ship.edu. Later we decide that we would be better off splitting the machine up, so we can simply create another machine and call it the mail server and rename the alias from mail.ship.edu to make it point at a different machine. Aliases can also make it easier for doing like automated systems administration tasks. For example, if Sloop were just one of several virtual machines on a physical server, we could create aliases like VM0 guest 0 or VM0 guest 1, and then it'd be really easy to monitor those. For instance, we could just write a script that does a for loop and it checks VM0 guest 0 through n. And reports the status. It doesn't have to be that that's what the rest of the users call that machine. It just makes it easier for us as systems administrators. The DNS also creates service descriptors for domains. For example, your email address is probably something like ab1234@ship.edu. But there's not a machine on campus that actually has that as its name. Instead, when the mail servers look for that domain name, they're going to ask the DNS for a mail exchanger. In other words, who handles mail for ship.edu? And the DNS is going to hopefully have a record for that. If it doesn't have a record for that, you can't send email to it. DNS also has support for load balancing. And I mean this, in this case, I mean load balancing for the servers that it resolves names for. So a given name can have many IP addresses associated with it. And the order in which those names are kind of returned by the DNS server is randomized, or maybe it's given in a round-robin nature. Using this strategy, now we can have several physical machines that each have an alias of www.ship.edu. And then the DNS is just going to rotate and randomly give me one of those different machines each different time. And so theoretically, as I have users looking up and hitting one of my web servers, they're going to get a different machine and kind of spread the load out evenly. To pull this off, the DNS is architected in a very special way. It is what we call a distributed and a hierarchical database, and so it's not like some SQL database that we've seen before. We'll look at the root servers that maintain the kind of top-level domain information, and then we'll kind of work our way down to the more local servers. By design and kind of at its core, there are 13 root server clusters that service the entire internet. Each of these 13 clusters is managed by a designated operator. Some of these operators here on this list are maybe familiar to you. For instance, NASA, the U.S. Army Research Lab, VeriSign. Those are all pretty familiar names. ICANN we've actually seen before. That is the organization that assigns numbers to internet clients. University of Maryland. So there's some familiar names in here. It used to be that all of these operators were solely U.S. companies, and they were controlled by the U.S. companies and thus the U.S. government. That has since changed. Some of these organizations now, I believe, ICANN is an international company. I believe RIPE is as well, but I'm not sure. I have to double check that. But what's interesting is we are talking about a cluster. So although there are only 13 unique IP addresses, there are 1,086 instances of computers in the world that use one of these 13 IP addresses. So what happens is we have these root servers spread around, typically at the Internet Exchange Points, the IXPs. And what's going to happen is when you have a machine that is responding to one of these IP addresses at an Internet Exchange Point, then that traffic doesn't need to get peered and sent out over another network and can just be responded to by that clustered computer. So this clustering is also a really important part of the design of the DNS. Ultimately, the goal here is we need to be able to spread out the DNS across all of these clusters, all of these computers, all of these different groups, not only for kind of load balancing and performance, but from security as well. If, for instance, somebody were able to take out these 13 IP addresses, then the internet as we know it shuts down. The only way that you'd be able to access any services is if you happen to know that Sloop's IP address is 157.160.36.12. Yeah, I actually happen to know that. And if you ask me in class during one of our lecture sessions, I'll be happy to explain why. But the short answer is because I'm old. So what's going to happen is if I have a computer that's trying to resolve like Google.com, my local DNS server here on campus has no idea how to get to Google. Instead, what it's going to do is it's going to pass it up to the root server, and it's going to ask the root server, who handles .com? And the root servers are going to tell me who handles a .com address. And so that's going to give me a pointer to one of the top-level domain handlers. As of 2020, there are 5,635 top-level domains. And by top-level domains, you can think of the generic ones like .com, .edu, .gov. But then there are also ones for each of the different countries. So, for instance, there's a .uk, there's a .us. Now there's like some really crazy ones. So there's like .biz. You name it. They expanded the number of top-level domains about 10 years ago, and they've just kind of ballooned into this whole hot mess of top-level domains. For each of the principal top-level domains, there are 13 server clusters that will resolve names for each of those different TLDs. So for instance, there's 13 servers that handle .com, or clusters that handle .com. There's 13 clusters that handle .edu. 13 apparently is a common number. And part of the reason why 13 shows up here is because 13 IP addresses happens to fit inside a single UDP message. And so this is one of those interesting times where, for performance reasons, the applications engineers paid attention to what does one packet of the transport layer hold. Let's fit our message inside one packet so that we don't have to send 2 packets for every request or 100 packets for every request. So this is really interesting, but let's take a look at some actual performance. Let's take a look at this rootservers.org. So rootservers.org is kind of a website that monitors the status of the root servers. And what it's showing here is the distribution globally of the 1,086 clustered computers. So for example, up here in Iceland, we have 6. Oh, look at that. We have 1 in Greenland and 5 in Iceland. The map was deceiving us. And so we can see here that Europe has a whole slew. If I zoom in, we can see that Europe does in fact have a whole slew. There's 47 cluster computers in Great Britain. There's some here way up in the northern parts of Norway. I'm sorry, that's Sweden. I don't know my map. Anyway, it's kind of interesting to see the distribution. We can even zoom in a little further. These letters are just showing us which of the 13 domains. So there's an L server, which is the ICANN. There's an F server, which is the Internet Systems Consortium. There's a K, which is the RIPE NCC. And there's an E, which is NASA Ames Research. So yeah, NASA's maintained a pier here in Hamburg. And Hamburg is one of Germany's big telecommunications hubs. So I'm not surprised to see that. Down in the bottom part of the screen, we can look at the 13 root servers and we can see information about it. So for instance, there are 53 locations, 53 hubs of the A root server. If we click on statistics, we can get an idea of how many queries these servers handle. So when we're looking at, let's see, where we are right now, 7,815 UDP queries, but that's millions. So we're talking 7.8 billion queries per day to these 53 these poor, sad, overworked 53 computers. We can kind of poke around. Let's take a look at the C group and just see what their statistics look like for comparison's sake. Oh boy, let's take a look. I don't know. So here in North America, it looks like they are doing 50,000 queries per second. So if we multiply that out by the like 68,000 or whatever the number of seconds per day is, it would tell you basically how many queries these things have. And I mean, they're handling a huge amount of traffic. So these root servers are not small, trivial little things. They are literally handling just about every single request on the internet has to go through these at some form or another. So if you get bored, take a look at this root-servers.org, and you can really see some interesting information. Let's go back, now that I'm thinking about it. Let's just see if we can go back to the US. And let's see, so there are 3 servers here in Pittsburgh, and there's 1 root server here in Philadelphia. And so it's kind of odd that there would be that many in Wilmington. Okay. And then there's a whole bunch in Washington, D.C., which kind of makes sense. There's a lot of communications hubs. And actually, Pittsburgh makes a lot of sense as well. Pittsburgh is one of the telecommunication hubs for the country. So really kind of interesting looking at some of the geographic distributions of these different servers, especially when you think about how far away they are. Nope, there's none in Antarctica. But they do try to put them into kind of geographically disparate places, and there's good reason for that. By spreading out these root servers across the physical world, not just the internet world, we are protecting the naming system from just about any type of natural disaster or man-made assault. So the idea here is that by having servers, for instance, way up in the Arctic Circle, if there was some kind of natural disaster down toward the equator, you have thousands of miles of separation between them. So the top-level domain servers are the next level of hierarchy. These services direct DNS lookups to an authoritative server for a particular domain. So architecturally, they're very similar to the global root servers. Again, we have 13 clusters. Each cluster can be replicated around the world. There's less public information about these because the registrars of these top-level domains maintain their own database and their own rules for who can be a peer. EDUCAUSE is an advocacy group for technology and education, and it manages all of .edu domain name assignments. And so kind of hard to find really a lot of information about how they resolve names. But for this example, we have .ship.edu as our domain name, and to get this, we were the first ones to ask for it. So back in the early 1990s, someone on campus, as we were getting ready to get on the internet, registered the name with EDUCAUSE, and that became our domain name. I guess if we were really sneaky, we could also have asked for like millersville.edu, and if we were really mean-spirited, we could even point that at a fake website that didn't make them look in a favorable light. So Millersville would probably they'd take umbrage at that, and so ideally EDUCAUSE will police those domain registrants and deal with conflicts and kind of remove registrations if they are malicious. But ultimately, every TLD registrar has its own process for dealing with conflicts and dealing with trademark violations and things like that. So what's going to happen is when one of EDUCAUSE's clustered computers receives a request for .ship.edu, it doesn't know how to resolve that specifically. But it does have a database of authoritative servers for domain names that it manages. And so what will happen is the EDUCAUSE cluster will return back the name or the authoritative server's IP address for Shippensburg. And so then there's one more domain name request that gets made directly to one of our name servers. And so it's this hierarchy that allows us to respond to these requests. But why do we have this middleman? I mean, it just seems really kind of complicated. It turns out that this is the classic divide and conquer approach for solving a big, hairy problem like this. Consider the split between the root servers and these registrar middlemen. While there are only about 5,800 top-level domains on the internet right now, there are literally millions of different domain names in each of these top-level domains. And by splitting the name lookup by top-level domain, the root servers only have to kind of point at one of these 5,800 top-level domains, which is a much faster thing. It's a much more manageable thing to do. Each of the top-level domains is only responsible for their registrants, and so the EDUs don't have to answer .com or vice versa. And so the load of doing the next lookup is then spread out over that top-level domains cluster. Now consider the split between the middlemen and the lower-level, more direct institutional or corporate name servers. Think about the billions of host names that are contained in those databases. Not only would one top-level domain need to be able to hold all of those billions of records, but databases get slower with the more data that they have to store, and so this is going to slow down the response time. Every lookup is going to be quite a bit slower. Further, there's going to be a near constant stream of changes to the database as every institution adds new machines or deletes machines, modifies some DNS entry. So by making this what we call a federated database, for instance, Shippensburg maintains its local database, and the rest of the world just kind of points at it when they reference us. This allows us to make changes without having to like pick up the phone and call somebody at EDUCAUSE and say, hey, we just bought a new machine from Dell, we need a new IP address and a new name. Like, that's just not really all that useful. So let's take a look at using some tools. So one of my favorite tools for this is called NS Lookup. And so if I'm using a terminal window, I can simply type in nslookup google.com, and it's going to simply tell me what the name servers are. And so what I see is that Google comes back and says 1, 2, 3, 4, 5, 6 different IP addresses, version 4 addresses for google.com, and 2 IP version 6 addresses. What's really interesting is NSLookup allows you to kind of mess around, and for instance, we can say, I want to use a different name server. So I think it's Google that maintains the 8.8.8.8 name server. So if I type in google.com here, now I only get one answer, and it says it's non-authoritative. So actually, these are all non-authoritative as well, because they're not the authoritative server. So it's interesting that using Google's own name service, I get a different set of responses using this 8.8.8.8. I'll have to look into that. I didn't expect that. I should have tried this ahead of time, I guess. But you can do other things. So like we can say set type equals any, and I could ask for ship.edu. And when I ask for ship.edu, what 8.8.8.8 tells me is that our name server is ns1.ship.edu, and that's its IP address. And we have information, for instance, like how long entries live in this database, like how long do they expire. We have stuff like, apparently this must be our Microsoft sign-on information in here, some kind of key that goes along with that. So services can request these special records out of our DNS entries and use them for configuration data. Here we can see that I have 2 mail exchangers for the ship.edu domain address. And one of them is, they're both Barracuda networks.com. So it looks like all of our mail first goes to this Barracuda Networks, and then it gets delivered someplace else. So, you know, sometimes when you're just trying to figure things out, using the DNS is an interesting starting point for learning more about an organization and the services that it provides. Another neat tool that we can use is provided kind of free of charge by this company called Newstar. Now let's bring them up. And what we can do here is we can use like this DNS traversal tool. And so if I go to google.com again and I ask it for some information, what we see here is the results that came back from the root server. So the root servers, I got results from all of them, not necessarily in the same order. It's interesting that the slowest one took 195 milliseconds. That's pretty slow, really. But then once I got to the top level domain, we can see how each of the top level domain servers responded for the .com. And in the best case, looks like 2 milliseconds is the winner. Oh, there's a 1 millisecond. And then the slowest was 32 milliseconds. Then we got 4 different name servers back from Google, and so this Newstar will tell us how long it took each of the individual name servers from Google to reply. Now, these delays are just like any other nodal delays that we've seen on the internet so far. So, for instance, the path that I took to get to one of these servers, all of the different hops along the way, is going to be additive. The same thing is going to be true if my name service is going to be stuck waiting for the root server for almost a fifth of a second. I'm going to notice that. Let's do this one more time and see. It's a little bit better. So 79, but we got a different root server to respond that time. 1 millisecond. That's even better. So if it takes 1 millisecond to hit the root server and it took 2 milliseconds to get a result from the .com server, and it took 10 milliseconds to get from Google, that's going to add up to be 10, 2, and 1, 13 milliseconds of just waiting for the DNS to respond. I haven't even been able to find the web server that I'm looking for to open a connection to it and get started. So all of this is going to add delays onto what your remote users are going to perceive of your system's performance. And so being able to get these resolved as quickly as possible is really, really important. They'll even give you a kind of an average of the DNS root server speed here. And so different servers, different routes, different paths, and they all kind of have different profiles. So it's kind of neat to be able to see some of this stuff and how it works out. So finally what's going to happen is once we get to that local organization-owned, publicly facing DNS server, now we can basically do what we want. We can create as many or as few records as desired. We can even allocate subdomains. So like the engr.ship.edu is a subdomain. So the campus server says, I don't know how to respond to an engr.ship.edu address, but I do know the machine that does, so talk to it. And so each of these different subdomains can have their own name services. So for instance, our subdomain is going to advertise our Microsoft credentials for our domain, the CS or the engr.ship.edu domain controllers, as opposed to the campus domain controllers. So graphically what this looks like then is we have really 3 layers that we're going to have to go through. We're going to have a root server that's going to figure out how to respond to a top-level domain. And it's going to tell you, I don't know, but go talk to this guy. The .org, for instance, is going to be handled by one of the 13 .org servers. And that .org server is going to say, I don't know how to find www.ieee.org. Go ask that guy. And that guy, in this case, should be the DNS server for the IEEE, and when I ask it who its web server is, hopefully it'll tell me. And so you have these 3 layers, the root server, the TLD servers, and then the authoritative servers. When we do a lookup in DNS, we have the possibility of different types of records, and we've already kind of seen that a little bit with those MX records, the mail exchangers. We can also have those text records. But mainly what you're going to see is an A record, which is a host name and its IP address. So for instance, if I were to look in the DNS file for Sloop, I would see an A record for Sloop and then its IP address of 157.160.36.12. We might also see an NS record, which is going to be the name service for a particular domain. And so this is basically just going to say, this is one of the machines that you should ask if you're trying to resolve a name. We also have a CNAME, which is also known as a canonical name. And this is going to take an alias and tell you what its real machine or the canonical name for that machine name is. So if Sloop were our web server, we might have a CNAME of web.engr.ship.edu and say that that is equal to Sloop. The MX, of course, is the mail exchanger, and it's just going to have say, this is the machine that handles the mail. What's interesting is this time to live value that's stored there, and I didn't really mention it before, but it's a good time to bring it up. If the internet had to look up everything all the time, we would be spending a lot of our resources maintaining a global DNS. And so what's going to end up happening is the name servers along the route are going to try to cache their results, and the root servers have nothing to cache. But the .com server, if you're asking it for .google, it doesn't really have to look into its database really far. It doesn't have to stride the whole database. It's already retrieved Google, and it's like on the top of mind. It's just going to be able to give it to you. If you ask your local name server for google.com, your local name server probably already has it. If it doesn't, it'll ask for it do all the negotiation the first time, but then it's going to hold that entry until its time to live expires. So let's say that Google says, we don't make changes very often. We're going to only make changes once a day. So if you get an entry from us, it's going to live for 24 hours. And so what that tells the name server on our machines here on campus is if you've found an entry for google.com, just hold on to it. Hold on to it for 24 hours. It's valid. Google said it's valid. And so we will continue to use that address over and over and over again and not have to go through all of this renegotiation. Now, once the time to live is expired, then that entry falls off of the cache and we have to go through and pull it again. So as we said before, database lookups in DNS are reverse hierarchical. Local machines ask their DNS to resolve a host name. So I start locally to get to the top level. My local DNS server is then going to retrieve information from the root and get that TLD server, and then I'm going to then directly talk to that TLD server to get the authoritative server, and then finally my local DNS server is going to hit that authoritative server and then cache the results as well. So what this does is it enables each domain to maintain their own list of machines. The caching kind of offloads some of this stuff, but we still saw billions of requests per day. And what ends up becoming, result of all of this is that the root servers are still the most critical, protected, and centralized resource on the internet. This is one of the few places where the internet has an absolute centralized hierarchy. And if that hierarchy were to be broken, the whole internet begins to fall apart. So after that deep dive into DNS, let's shift gears a little bit and take a look at the final protocol topic in this chapter, and that's peer-to-peer file distribution and how peer-to-peer networks impact network transport. Recall that there are really two general ways to organize a protocol. One is called client-server, and things like DNS are certainly client-server. And then the other is peer-to-peer. Peer-to-peer, or P2P architectures try to make minimal reliance on the always-on, centrally managed servers that we find in client-server. The classic example of a P2P architecture is BitTorrent. The BitTorrent architecture uses peers to distribute contents of files. Because each peer is pushing out data to each other, it becomes very hard to fully saturate any one link. And the idea is if there's going to be anything saturated, it's going to be your download link. Of course, it should be noted that while BitTorrent does improve performance, it does not mean that peers are anonymous, nor does it mean that the torrent distribution network is any more reliable than the client-server version. And we'll take a look at this in more detail later on. Let's do a little math. If the goal of peer-to-peer network is to remove the bottlenecks created by a central server, and then the congestion of that central network, then we should be able to quantify the improvement in performance, not just say it feels like it should be faster. Let's see if it really is faster. So to do that, what we need to consider are some basic math. Let's represent the relationships between computers, servers, and the internet as in this figure. We can represent U sub I and D sub I as the upload and download speed of individual computers on the network, on the internet. We represent the thing that is being downloaded as a generic file, and we're going to say that it has F number of bits, and we're using bits here just to kind of keep the units together. Finally, we track the number of peers or clients that are trying to retrieve the file at any one time. Let's first study the client-server model, since we kind of mentally, I always think that that's a little bit easier to understand. At best, the server's upload speed is better than anyone else's, combined. And if that's true, then it becomes the minimum time for an upload. In other words, we can't upload a file to any one client any faster than the server's upload speed. So the distribution time must be at least the number of bits times the number of clients divided by the server's upload speed. So this is assuming, for instance, that I have like a 500 terabit upload speed to the internet and everyone's using modems to download this file. We're not going to saturate the network. However, in the worst case, we have to wait for the slowest client. So the total time to distribute the file to all clients will now be no worse than grandma and her 2400 baud modem or whatever we have. So what we end up with is this relationship that the distribution time must be at least as bad as the maximum of those two things. So either we've saturated the server's upload or we've saturated one of the client's download speeds. So as homework, we're going to be looking at trying to find a lower bound for all of this. And we're going to try to explore what happens if the total download speed is way bigger than the upload speed. Then we start to have some interesting limitations. But this DCS is the worst case, or the best case distribution. It can't be any better than either of these two. I just realized what I said. Yeah, the time can't be any less than either of these two. It might be higher, it could be far worse than this, but it can't be any lower than this. The initials, okay, so here is the peer-to-peer arrangement. There is going to be some cost to upload the file to the first peer, and that's going to be at least as bad as the cost to send the first file. After that, the slowest peer is going to set the minimum time. So the time must be greater than or equal to that peer's time and its ability to download the file. So here we see that the download rate is going to be used to figure out the speed of that one peer. However, the fastest peers can download based on the aggregate bandwidth of all of the other peers. So the aggregate time has to be at least that bound. So here what we're saying is, let's say I have one peer with FiOS 10 gigabit fiber at home. I can just suck down from all of the peers as fast as possible. And so that's going to be the aggregate upload rate. And now what we have is a very simple relationship that the minimum time for peer-to-peer has to be at least as bad as the time it takes to upload the file in the first place, plus the maximum time of either the slowest peer or the aggregate download speed of everybody. So let's say that we have a network with really terrible upload speeds, like everybody's on a DSL modem. That might actually be slower than the slowest download speed. And so this term kind of takes into account bad upload, this term takes into account bad download. All right, so what we can do is we can run some scenarios. So in this first scenario, what I've done is I've put in a number. So our server upload speed is a gigabit per second. That's 1 times 10 to the 9th. I'm using MATLAB here, by the way, MATLAB live script. I'm setting the download speeds for each of my 6 clients as 100 megabit, 25 megabit, and so on. The upload speeds are 100 megabit, 300 megabit, and so on. Some of them are better, some of them are worse. The size of the file is the average size of a movie. It's about 4.7 gigabytes, but I'm multiplying that by 10 to get bits. And then I have the length is the number of clients, 6 in this case. So then I can compute these terms for the client server. I can compute these terms for the peer-to-peer. And sure enough, in this small example, because I have so few clients, their aggregate bandwidth doesn't exceed the server's speed, and so peer-to-peer actually wins or loses. Client server wins. It has a lower time, but not by much. I mean, this is seconds, so this is actually still pretty pitiful. If we change things up a little bit, let's say that I have 25 clients. Everything else is the same. Every client has a 100 megabit download and a 50 megabit upload. If we do that, now we see that the client server is actually slower than the peer-to-peer. So at some point there's going to be a point where peer-to-peer wins. And somewhere between the 6 clients and the 25 clients, we crossed over that point. And so we can look at this and kind of decide, if this is what we're trying to model, then we can see which one's better. Finally, what I did is I used LiveScript and I made functions for the client-server calculation and the peer-to-peer calculation. And then what I did is I just iterated over different numbers of clients. So this is keeping the same download of 100 megabit, the same upload as 50 megabit, same file size, store them into an array, and then plot them. And this red line we see is the client server, and after a point, once we've saturated that upload speed right here at about 10 clients, and that makes sense, the download speed. At 10, we've maxed out the server's upload connection. Now everybody's just slowing down, and it's just going to be linear growth. Whereas here, we're still dominated by the time that it's going to take to upload the server once we get it started, or the file once we get it started. So as a discussion, both analyses here set the lower bounds of the time. We can show with some interesting proof theory that both lower bounds are achievable. The client server centralizes loads, and so it demands higher bandwidth networks in the server. Remember that the cost to upgrade these networks and these servers is super linear. So doubling the capacity of the network is going to be like 10 times the cost. Adding more bandwidth can saturate a server, and adding more server can saturate a bandwidth, and so it becomes an arms race. On the other hand, peer-to-peer distributes the loads kind of organically, but at the cost of the inability to control the number of active peers. Popular downloads might have hundreds or even thousands of concurrent peers. Others, maybe only one or two, and so then you're kind of stuck. Content providers can't control this either. Like, content providers would have to put thousands of servers around the internet to be able to manage this, and then you're back to almost as much money as what you'd invest in a centralized client server. Peer-to-peer also really suffers when you have a bunch of people who are doing what are called asynchronous sharing. They're downloading but not sharing anything back. We call them leeches. So as I mentioned before, BitTorrent is probably the most popular peer-to-peer file sharing protocol around. Peers in a torrent share equal-sized chunks of files, typically 256 kilobytes. Each torrent has a tracker node, and that tracker node is almost like a central server. So even though we're doing peer-to-peer, we have a little bit of information. But as long as the tracker is up, the whole torrent is up. But this tracker isn't serving the data like it would be in client server. As new peers join the tracker node, the tracker can advertise their status and what data that they have available. Peers then can read off of this tracker node, and then they can pick the highest bandwidth neighbors, and then randomly as they're downloading, they're going to kind of randomly pick new neighbors and see if those new neighbors give them any better performance, and if they do, then we'll use those as our best neighbors. And so we'll kind of eventually penalize freeloaders, we'll eventually kind of converge onto the most high-performing network nodes and be able to download as fast as we can. And so that's basically how BitTorrent is operating. I'll try to sneak a quick demo of it into these slides, although this lecture is getting a little bit long. Video streaming services is also in the textbook. I don't want to spend too much time here, but video streaming services are going to depend pretty heavily on these content distribution networks, which we've seen before a couple of times. And so if you really just kind of think about it, let's take a look at this next slide. Content delivery networks are placing these content servers into these internet exchanges or directly into ISPs. We have two strategies for that. One is this Enter Deep, which is used by Akamai and Netflix and some others, where we're putting them directly into ISPs. Whereas other content networks are trying to bring your connections onto a privately managed network very fast, and that's the bring home strategy. In other words, instead of paying Verizon and L3 and these different top ISPs for bandwidth, we'll just do our own. Google's a big proponent of this, and it's interesting that Google does both. The reason I bring this up is a company like Google has 14 mega data centers throughout the world, each one with about 100,000 servers each. And then they have 50 clusters, I'm sure there's more today, but that are scattered directly into the IXPs. And each of those clusters is about 100 to 500 servers. And each of those are used to kind of get your bring home connections into Google's network as quickly as possible. Finally, Google also has hundreds of enter deep clusters that are trying to serve content directly from ISPs. And each one of these is going to have maybe tens of servers in each location. Why do I bring this up in the context of peer-to-peer? Because effectively, Google has built its own peer-to-peer network. Instead of having one central server or one group of servers at one location, they have distributed across the world, across hundreds or thousands of peer points, and they're able to kind of flood the local network with Google traffic. And so they can centrally manage their Google backbone, the stuff that they own, and then they can inject results right to their end users. And that's one reason why Google is so reliable and it's so fast. They've invested billions of dollars into building this almost parallel internet that has thousands of peers serving all kinds of data. If we look back at Netflix, for example, Netflix is kind of similar. Netflix is based on Amazon's cloud computing for kind of the daily operations of things. So, for instance, when a studio wants to upload a new movie to Netflix, they will do what's called an ingestion. They will ingest the movie and then turn it into different formats for all of the different content formats that Netflix serves. Different qualities, different versions, even different editing times. And then this Amazon Cloud can also then be used to feed the content delivery network that Netflix maintains that we've already talked about, which is their Open Connect servers. They use Akamai, which is another content distribution network to distribute like web pages. So when you first go to Netflix and you see like the list of content and you kind of browse around, that's coming from one of these content delivery services. Netflix has a presence, published presence in at least 50 locations directly in one of the main IXPs. And they have thousands of these Open Connect servers, again, almost forming like a peer-to-peer network. Only in this case, the peers are just very physically co-located near their users. And it load balances and distributes the network. So that was part 3. I know we spent quite a lot of time on DNS and streaming. I don't want to make this thing too long, so we will do some examples of some of this in a different lecture, or maybe we'll do it in class together.